Welcome back, everybody. We have our wonderful picture here. I do want to spend a little more time talking about our wonderful picture this time. In the middle, in the center, we have our regular expressions, our regular languages. NFAs and DFAs are simple machines. And then we expanded that picture and started talking about grammars, context-free languages, and PDAs, machines with stacks, infinite stacks. We didn't talk about LBAs, but we will. And then out here in these bubbles are our Turing machine related circles. We are going to clarify this picture, some of which you will understand at least ever so slightly on the tinges of your knowledge today. That's where we're headed, is to start to get a fuller picture of this picture today. In order to do that, I first want to talk about all the things that make Turing machines really cool, so that as we begin talking about Turing machine languages and algorithms and things like that, they are easier for us to do things in. Much like a function in a programming language makes doing the same thing over and over again easier, we're going to lean on that sort of abstraction to make Turing machines easier for us to deal with as well. All right, so to start, Turing machines have a few predecessors or archetypes in a sense. One of them is this linear bounded automata. And what's different about the LBA than the PDA or the Turing machine is that it can't write beyond its input tape. So think of it like a Turing machine that has a tape with the input written on it, but it's not allowed to use infinite memory. It has this linear bounded memory. It can only go as far as its input. This creates a class of languages called context-sensitive languages, which do have grammars. We're not going to study them. They're more powerful than context-free languages, but they're not as powerful as Turing machines, which has the infinite tape. But there are some things that are interesting that are more powerful, or the same power, I should say, as a Turing machine. So if you take a PDA and you give it a second stack, it has the same power as a Turing machine. If you take a Turing machine and you give it an extra tape or a million extra tapes, it has the same power as a Turing machine, which starts to become really, really useful if you want to do something like think of one of those tapes as a variable that will remember something for you. You can make Turing machines that are transducers, or basically their job as a Turing machine is just to alter the tape. So one thing that you might do in one of my homeworks in my class is write a transducer that will take a tape and as a binary number, treat the input as a binary number and add 1 to it, right? So you can kind of write a subroutine in a sense where you have an add 1 Turing machine. Non-determinism doesn't make Turing machines any more powerful, so you can do a thing like say, hey, try all 16 of these things at the same time, and if one of them works, give me that one. So if you wanted to do something like, I don't know, do the satisfying language using 3 variables, try all possible values of true and false for all 3 of those variables, which are 8 values, and then tell me if one of those satisfies some Boolean equation. You could do that non-deterministically, trying all 8 at the same time, or guessing all 8 at the same time. And lastly, this concept of a printer TM is going to keep coming up. It's pretty important. A printer TM is something that's going to print all of the strings in its language as opposed to trying to accept them. So you can imagine trying to accept 0 to the n, 1 to the n like we did in the last video. We wrote an algorithm to do that. Instead, we could have written a printer TM to print every string in that language. You know, like the first time it prints the empty string by printing nothing. The second time it prints 0 and 1. The next time it prints 0, 0, 1, 1. You can imagine we could enumerate every string in the language. And that's a printer TM, which is a way to describe a language using a Turing machine without using the kind of traditional methods of a Turing machine. These variants all kind of combine together to give us more power and give us more maneuverability using Turing machines. But where Turing machines start to get really interesting is when we start passing them as input to one another. So that's when things start to get interesting. So before we can actually get there, I want to introduce you to a situation that kind of, well, maybe I showed you a little too much. A situation that kind of highlights this, which is the Goldbergs conjecture. The Goldbergs conjecture says, roughly, that every even number, let's ignore negatives, greater than 2, is equal to the sum of 2 primes, right? So you could start by saying, hey, that starts at 4. 4 is 2 plus 2. And if you would like, you could try this for a few others for yourself. So 6 is 3 plus 3. 8 is 3 plus 5. And there is actually some neat symmetry that's happening here. What's really, really cool about Goldbergs conjecture, if you want to pause and try this for a while, go ahead and do that, is that we don't know whether this conjecture is true or not. That's what's really cool about Goldbergs conjecture. It's probably like one of the most oldest unsolved problems in number theory. And you could write out a whole bunch of these, and you could go on till 10 to the 5th, and you would not be the first person to do this. Or even, I think, 10 to the 18 or something really, really high up there, using distributed computing power. So there's lots of other work related to Goldbergs conjecture, but we're going to use this as kind of a toy problem to talk about how Turing machines do some things. So think about how you might write a computer program to exhaustively print the answers like we did up here. How would you write a computer program? What do those loops look like that could exhaustively print every situation like I did up here? Think about that. Maybe pause it. Maybe sketch some things out. Okay. Hopefully you're back. That algorithm starts to look something like this, right? You've got a list of primes. You're writing some loop that increases by 2 every time. You're going to walk through those list of primes, and you're also going to walk through it again, and then you're going to see if their sum equals the number you're looking for. So I'm going to start with 2, and then I'm going to try 2, and 2 plus 2 is 4. So I know that 4 is done. And actually, I say square root of n here. That's not quite right, is it? No, it's not. Let's just say up to n. That's fine. And we just do this forever. And as we continue through the loop, moving up to the next number, we're going to check to see if we should add something new to the primes. And we'll just continue to do that. I am skirting over a lot of things here. And you might think of this as kind of like a printer TM that's exhaustively printing all of these sums that work for all numbers, right? If you wanted to flip this and say, I'm actually looking for a counterexample, why don't you pause and think about what a program like that might look like? Go ahead and pause. Hopefully you're back. What does that look like? Well, it's really kind of the same, except you probably add something in here like, if I didn't print anything, that's hard for me to write here. If I didn't print, then it's a counterexample, right? So why is that important? That is important because we actually don't know, because we don't know if Goldbergs conjecture is true or not. We actually don't know if this will ever print, which is really kind of amazing. Oh, it's so cool. So if such a counterexample exists, this Turing machine that we're writing here, and again, we kind of wrote just pseudocode, but hopefully as you think about how those variants work together, you could see how the pseudocode could work. So what happens to this Turing machine if no such counterexample exists? Well, if it exists, it's going to halt, but if no such counterexample exists, then this Turing machine is going to loop forever. It's going to hunt forever for this counterexample, and it's never going to find it. Why is that important? Well, what we've done is we've come up with a useful Turing machine that never halts. And the way I think I would say this, to kind of make sure I'm guiding you into the direction that I want you to be, is, we don't know whether Goldbergs conjecture is true or not, but if it's true, the printer TM algorithm actually prints everything in the conjecture. But if it's not true, the printer is going to miss some even numbers. But more importantly, when we do the counterexample hunter, it will never halt. Now, we expect it not to halt if Goldbergs conjecture... Wait, I have this backwards. If it's not true, the counterexample hunter will halt. But if let's erase this word never. But if Goldbergs conjecture is true, the counterexample hunter will never halt. And that's kind of important because we don't know which of these two worlds it lives in. I wouldn't say this is a Schrodinger cat situation. It's just we don't know. Like, we have run this program for as long as it will run, and it never found a counterexample, right? Like, we've done this. This is a thing that has existed. Otherwise, if we had found a counterexample, we would know that the conjecture is false, and it would no longer be something that we need to talk about so much. or at least not in the same way. We would probably talk about other things related to it still, and we will do that for a long time for sure. So what's my point? My point is, there's a situation, and I say either way here, that's not quite right. There's a situation where the counterexample never halts, and for now, we don't have any way to know if it will. And this leads us to interesting distinguishing characteristics of some Turing machines. And so I'm going to describe two languages, or two types of Turing machines maybe, that describe two types of languages right now that are going to be used for almost the rest of our videos to describe interesting things. There will be some diversions here and there, but these two words I'm describing here early because they are that important, okay? And they are, a Turing machine is decidable if it can halt, either accept or reject, any input given to it. So if I have a Turing machine that always knows how to halt, then that Turing machine is decidable. A language is Turing decidable if there is some Turing machine that decides it, right? In this case, this language of the Goldberg conjecture, we actually don't really know whether it's Turing decidable or not, because we don't know if that counterexample can ever halt. We can accept strings in the language easily enough, and we can reject strings in the language easily enough, but at the same time, if we said, like, is the counterexample language empty or not? Well, we don't know, so we can't answer that. Anyway, this becomes important later. I know you can't see it yet, but there are lots of things that are decidable that are amazing. Like, does a DFA accept or reject a string? Maybe we can figure that out. But there are lots of things that aren't decidable, which become more and more important as we move on. We're not ready to describe most of those yet, and so for now, I'm just pitching this out there, right? And if the Turing machine can always halt, then it's decidable, and any language that has a decidable Turing machine is a Turing decidable language. Now, there are other languages such that you can always halt and accept on its input, but when you go to reject, maybe you get stuck in a loop, or maybe you can reject sometimes, but not all the time. And so sometimes you might loop forever. And so any Turing machine that can always accept, but sometimes gets stuck in a loop, or sometimes it can reject, is Turing recognizable. Now, anything that's decidable is recognizable, because if you can accept and reject, then you are definitely recognizable. But recognizable languages, some of the recognizable languages are not decidable because we can't necessarily reject strings in those languages. And we are going to get to those, and those are really, really cool. It's where we're headed. Now, anything that has a printer TM is a recognizable language. So if you can make a printer TM is a recognizer in a really cool way, because what we could do is let the printer TM run and then check our input against the printer TM's output. If they match, then we can accept. And if it doesn't show up, then we wait forever to see if it ever will show up. And if it doesn't, well, we're still waiting because we have to get to forever first, right? So printer TMs are an example of things that are Turing recognizable. Like, if you can enumerate all the strings in a language, you know at least that you can accept all the strings in the language. And you might be saying, but hey, Doc, like, it's kind of silly to talk about strings that may or may not be in a language, and that you'll have to wait for next time, because that's as much time as we have for this time. All right, so we're going to stop it there. As always, be kind to each other, and in order to do that, you have to be kind to yourself. See you all next time. Bye.